Most people think they know why a bicycle stays upright, but the explanation you've been told is incomplete and in some cases simply wrong. If something as ordinary as a bicycle can fool millions of intelligent people, imagine how many other obvious truths deserve another look. Stay with me until the end, because once you understand what is really happening, you won't just see bicycles differently, you'll begin to see how nature itself hides its deepest ideas in the simplest things. A bicycle is one of the strangest inventions ever created. Not because it is complicated, but because it is so simple that it hides its secrets in plain sight. Nearly everyone has ridden one, watched one, or at least knows what one looks like. Yet if I stopped 100 people on the street and asked a simple question, why does a bicycle stay upright? Most would confidently give the same answer. They would say, because the spinning wheels act like gyroscopes. It sounds convincing. It has just enough science in it to feel correct. It has been repeated in classrooms, documentaries, conversations, and even textbooks. But here is the surprising part, that explanation is not the whole story, and in many situations it is not even the main reason. That should bother us a little. Not because we have misunderstood bicycles, but because we have misunderstood something much more important. We often mistake familiar explanations for complete explanations. We hear an answer enough times that we stop asking questions. Curiosity quietly disappears, replaced by confidence. Nature, however, has a habit of rewarding those who remain suspicious of easy answers. Imagine seeing a bicycle for the very first time without knowing anything about it. You would notice two very thin wheels holding up an entire person. You would probably predict that the rider would fall immediately. After all, if you stand a bicycle still without anyone holding it, it collapses in seconds. It looks unstable because it is unstable. Yet the moment it begins moving, something remarkable happens. The same machine that refused to stand for even a second suddenly becomes graceful, balanced, and almost effortless to ride. Now ask yourself a different question. What changed? The bicycle did not suddenly grow wider. The rider did not suddenly become lighter. Gravity did not weaken. The only obvious difference is motion. Somehow, movement transforms an unstable object into one that can travel for miles while balancing a human being on two narrow lines of contact with the ground. For a long time, people believed they already knew why. They pointed to spinning wheels. If you have ever played with a spinning bicycle wheel while holding its axle, you know it resists changes in direction. Twist it one way, and it pushes back in an unexpected way. This strange behavior comes from angular momentum, and it is very real. So the reasoning seemed straightforward. The wheels spin. Spinning objects resist tipping. Therefore, spinning wheels keep bicycles upright. The explanation sounds beautiful because it connects a mysterious phenomenon to a well-known principle of physics. But science has a habit of asking uncomfortable questions. If spinning wheels are the real reason bicycles balance, then what happens if you weaken that effect? Should bicycles suddenly become impossible to ride? Researchers decided not to argue about it. They built bicycles designed specifically to test the idea. Some had wheels whose gyroscopic effects nearly canceled out. Others had unusual steering designs that challenged long-held assumptions. To everyone's surprise, some of these strange bicycles could still balance and be ridden successfully. Think about what that means. The explanation that seemed obvious could not explain everything. The wheels mattered, yes, but they were not telling the whole story. So where should we look next? Perhaps the secret is not in the wheels alone, but in the way the entire bicycle responds to falling. Imagine balancing a broomstick upright on the palm of your hand. At first it seems impossible. The moment it leans slightly to one side, you instinctively move your hand underneath it. You do not keep your hand still and hope the stick returns by magic. You chase the falling stick with your hand. In fact, you are constantly allowing it to lean while moving its base underneath the center of mass. Without realizing it, you are performing hundreds of tiny corrections every minute. A bicycle behaves in a surprisingly similar way. When a bicycle begins to lean, the front wheel naturally tends to steer into the direction of the lean. That tiny steering motion changes the bicycle's path. Instead of continuing to fall away from its center of mass, the wheels move underneath it. The bicycle is, in a sense, catching itself before gravity wins. This is a profoundly different way of thinking. Instead of imagining the bicycle stubbornly resisting gravity, imagine it continuously cooperating with gravity. It does not refuse to fall. It begins to fall, then immediately moves itself so that the fall is interrupted. Balance is not the absence of falling. Balance is falling in exactly the right way. That idea appears everywhere in nature. When you walk, you are not perfectly balanced. If you freeze halfway through a step, you would probably fall. Walking is actually a controlled series of falls. You lean forward, gravity begins pulling you down, and before you hit the ground, your foot lands beneath you. Then the process repeats. Walking feels stable only because your body keeps catching itself. Running exaggerates this even more. A bicycle simply performs the same dance with wheels instead of legs. But now another mystery appears. Why does the front wheel steer into the fall instead of away from it? The answer lies in geometry. Look closely at a bicycle from the side. The steering axis, the imaginary line around which the handlebars rotate, is not perfectly vertical. It tilts backward. The point where that axis touches the ground usually lies slightly ahead of where the tire actually contacts the road. This small distance is called the trail. It sounds like an insignificant detail, almost too boring to matter. Yet it changes everything. Because of this geometry, when the bicycle leans, gravity and the forces from the ground naturally encourage the front wheel to swing into the lean. No rider has to think about it consciously. The bicycle possesses a remarkable tendency to correct its own direction. It is almost as though the bicycle has learned a trick, not because it is intelligent, but because its shape quietly guides its behavior. This is one of the most beautiful lessons in physics. Sometimes the answer is not hidden in stronger forces. Sometimes it is hidden in clever geometry. Think about how often this happens elsewhere. An arch can support enormous weight, not because its stones are individually powerful, but because of how they are arranged. A suspension bridge carries thousands of vehicles, not because any single cable performs a miracle, but because each part shares the load in precisely the right way. Likewise, a bicycle balances not because one magical force keeps it upright, but because several ordinary effects cooperate in extraordinary ways. The spinning wheels contribute. The steering geometry contributes. The movement of the rider contributes. The flexibility of the frame contributes. Even tiny adjustments made unconsciously by your body contribute. None of these pieces alone explains the entire story. Together they create something that feels almost magical. This is often how reality works. We are attracted to simple explanations because our brains love neat stories. We want one cause, one effect, one sentence that explains everything. Nature rarely grants us that luxury. Instead, reality resembles an orchestra. No single instrument creates the symphony. Remove one violin, and the music continues. Remove the drums, and it changes but survives. The beauty comes from interaction. A bicycle is exactly like that. It is not balancing because of one hero. It is balancing because dozens of small physical principles cooperate so perfectly that our brains mistake the result for simplicity. And perhaps that is the greatest surprise of all. The bicycle is not teaching us merely about transportation. It is teaching us how to think. Whenever someone says the answer is obvious, that is precisely the moment to become curious. Because sometimes the most ordinary object in your garage can reveal something extraordinary about the universe. It reminds us that science is not the art of collecting answers. It is the art of discovering which questions we have stopped asking. The more carefully you look at a bicycle, the stranger it becomes. Suppose I asked you to design one from scratch without ever having seen one before. You know it has to carry a person, travel quickly, turn corners, and somehow remain balanced on two incredibly narrow contact patches where the tires meet the road. Would you naturally invent something that looks like the modern bicycle? Probably not. You might decide that 4 wheels are safer, maybe 3 wheels. You would almost certainly assume that 2 wheels in a straight line are asking for trouble. Yet after more than a century of engineering, the 2-wheeled bicycle remains one of the most efficient machines ever created. Efficiency is another clue that something deeper is happening. Nature often rewards systems that cooperate with its laws instead of trying to overpower them. Airplanes do not defeat gravity by becoming stronger than gravity. They use airflow to generate lift. Sailboats do not fight the wind. They use the wind from directions that seem impossible to move forward. Likewise, a bicycle does not conquer instability. It uses instability in a very clever way. Think about learning to ride one. Do you remember reading a manual before your first attempt? Did someone hand you a sheet filled with equations about angular momentum, center of mass, torque, and steering geometry? Of course not. Someone probably held the seat while you wobbled from side to side. You felt awkward. Every few seconds you tipped over. Then, after enough attempts, something remarkable happened. You stopped thinking. Your body began making tiny corrections before your conscious mind even realized they were necessary. This is one of the most astonishing abilities of the human brain. Long before you understand the physics, your nervous system has already solved it. Every second you're riding, your eyes notice the horizon shifting by a fraction of a degree. Your inner ear senses the smallest tilt. Your muscles respond almost instantly. Your hands rotate the handlebars by tiny amounts that are almost impossible to notice. Your hips shift your weight. Your shoulders move. Your knees adjust pressure against the frame. None of this feels deliberate. If someone asked exactly what you did to avoid falling 5 seconds ago, you probably couldn't answer. Not because nothing happened. Because thousands of tiny adjustments happen too quickly for conscious thought. Your brain is running one of the fastest feedback systems imaginable. Imagine trying to perform the same task using only conscious decisions. The bicycle leans 1 degree to the left. You notice it. You think about the problem. You calculate the correction. You decide to turn slightly. By the time you've finished thinking, you're already lying on the ground. Thinking is too slow. Instead, your nervous system relies on feedback loops that have been refined through millions of years of evolution. Feedback is one of the most powerful ideas in science. A thermostat measures temperature and adjusts the heater. Your body measures blood sugar and releases insulin. An autopilot measures an airplane's direction and makes corrections. Even your own balance while standing still depends on constant feedback. You may believe you're perfectly motionless, but sensitive instruments reveal tiny swaying motions all the time. Your muscles are continuously making microscopic corrections to keep you upright. Standing still is actually an active process. So is riding a bicycle. Once you understand feedback, you begin seeing it everywhere. Consider a tightrope walker. People often imagine that the performer achieves balance by becoming perfectly still. In reality, the opposite is true. A skilled tightrope walker is constantly moving. The long balancing pole shifts. The ankles bend. The knees flex. Tiny corrections happen every fraction of a second. What appears calm from a distance is actually continuous motion. The bicycle follows exactly the same philosophy. Perfect balance doesn't exist. Continuous correction does. Now here's something even more surprising. There are moments when experienced cyclists can ride without touching the handlebars. At first glance, that seems impossible. If steering is so important, shouldn't removing your hands guarantee a fall? Yet skilled riders manage it. How? because steering doesn't disappear. Instead of using their hands directly, they subtly shift their body weight. Those weight shifts cause the bicycle frame to lean, which influences the front wheel, which then steers naturally due to its geometry. The entire system continues working through a different pathway. Again, notice what's happening. There isn't just one solution. There are many ways for the bicycle to maintain balance, because balance emerges from the interaction of multiple effects. Scientists love situations like this because they expose a common weakness in human thinking. We like assigning credit to one cause. Reality prefers teamwork. Suppose you ask why a tree remains standing during a storm. Should you credit the roots? Certainly. Should you credit the strength of the trunk? Absolutely. What about the flexibility of the branches? Or the way the leaves allow wind to pass through? Or the soil holding the roots? Each answer is partially correct. But none is complete. The same is true for bicycles. Now let's imagine something different. Picture riding on the moon. The moon has only about 1/6 of Earth's gravity. Suddenly, your weight becomes dramatically smaller. Would balancing become easier or harder? At first, you might guess easier because you're lighter. But gravity is actually one of the forces that helps create the dynamics your bicycle depends upon. The entire interaction between leaning, steering, and correcting would change. You could still ride, but it wouldn't feel the same at all. The rhythm of balancing would slow down. Falls would develop differently. Every correction would happen on a different time scale. This thought experiment reminds us that the bicycle is quietly having a conversation with gravity every single second, not fighting it, conversing with it. Now imagine riding through a strong crosswind. Suddenly, an invisible force begins pushing you sideways. Again, your body responds almost before you're aware of the wind. You lean slightly into it. You steer differently. You adjust your posture. Within moments, you're riding normally again. Notice how flexible this system is. The bicycle isn't following a rigid program. It's adapting continuously. That adaptability is what engineers call stability, not the inability to move, but the ability to recover after being disturbed. A glass sitting on a table isn't interesting because nothing happens. A bicycle is fascinating because everything is happening. Every bump in the road changes the forces. Every pebble shifts the tires. Every turn changes the balance. Every gust of wind creates new challenges. And somehow, through countless tiny corrections, order emerges from what could easily become chaos. Engineers spend entire careers trying to build machines capable of this kind of behavior. Self-driving cars, walking robots, autonomous drones, all struggle with problems that your bicycle solves almost effortlessly, with a remarkably simple mechanical design combined with the incredible adaptability of the human brain. In fact, some of the world's most advanced robots still have difficulty matching the graceful balance of a child who has ridden a bicycle for only a few months. That should make us pause. Sometimes intelligence isn't about performing difficult calculations. Sometimes it's about responding gracefully to change. The bicycle teaches this lesson over and over again. It doesn't demand perfect conditions. It succeeds despite imperfect ones. The road is uneven. The tires wear down. The rider shifts position. The wind changes direction, yet the system keeps finding balance. Not once. Thousands of times every minute. And perhaps that's why bicycles continue to fascinate physicists, engineers, neuroscientists, and mathematicians alike. What seems like a solved problem at first glance turns out to be a beautiful example of how simple components can produce remarkably complex behavior. Every answer uncovers another question, and every experiment reveals another layer that was hidden beneath what once appeared obvious. So the next time you see a bicycle leaning against a wall or gliding quietly down a road, don't just see a machine. See a question. See a reminder that the world is filled with ordinary things hiding extraordinary truths. The bicycle stays upright not because of one magical force, but because countless small principles work together in perfect harmony. And perhaps that is the greatest lesson of all. Reality is rarely as simple as our first explanation. This is why science is so exciting. It doesn't ask us to memorize answers, it asks us to become comfortable questioning them. The moment you believe you've completely understood something, you've probably stopped looking closely enough. Progress has never belonged to those who accepted the first explanation that sounded reasonable. It has always belonged to those who were willing to ask, is there more to this story? That simple question has transformed our understanding of the universe. It revealed that Earth is not the center of everything. It uncovered invisible forces shaping galaxies. It showed us that time itself is not as absolute as it once seemed. Every great discovery began when someone refused to mistake familiarity for understanding. The bicycle is a perfect symbol of that journey. It reminds us that the universe doesn't reveal its secrets through complexity alone. Sometimes it hides them inside the simplest objects we pass every day without a second thought. A child riding to school, a commuter cycling to work, or an old bicycle resting in a garage, maybe demonstrating principles that connect mechanics, mathematics, biology, and human intelligence in ways that are still being explored. So never lose the habit of asking why. Never let a familiar answer silence your curiosity. The greatest discoveries are often waiting behind the questions everyone else believes have already been answered. Because the real difference between someone who merely looks at the world and someone who truly understands it is not intelligence, it's curiosity. And if a simple bicycle can teach us that, then perhaps the universe has been trying to teach us something all along. The deepest truths are rarely hidden in the distant stars. More often, they're quietly spinning past us every single day, waiting for someone curious enough to notice.